Okay, this is a supplemental lecture on network math and subnetting. I believe these are all problems we have done before, but it was useful to revisit them and make sure that you understand them. It's very important concepts. So starting with one of the very first network math type problems that we started with was given an IP address and a subnet mask. Can you determine the network address and broadcast address for the IP address? So in this case, we're given 172.20.30.40 and a subnet mask of 255.255.248.0. So what we need to do is the first question we ask is, what is the host's network address? So in this first example, we're going to go ahead and convert the IP address and subnet mask into 32 bits. Of course, you probably know that where most of the action is going to take place is in the third octet. That is the octet or byte that doesn't have 255 or 0 in it. So if we convert the IP address to binary, this is what we have. We'll leave the decimal points there just to kind of denote where each of the 4 bytes is. Then we need to take the subnet mask and convert it to binary as well. So the question is, how do we determine what the network address is for this IP? And the answer is we do a bitwise AND. So we've done a couple of things here from the subnet mask where all the string of ones changes to string of zeros. We know that the network portion is going to be on the left and the host portion is going to be on the right. If we go through and do our bitwise AND, this is the result we get. Another way to think of this, because we're ANDing with all zeros, is setting all the host bits to 0 would be an answer as well. If we convert that back to decimal dotted notation format, the network address for that IP is 172.20.24.0. Now then, the next question is, how do we get the broadcast address? And hopefully everybody said, or at least thought, by setting all the host bits to 1. So if we do that, we have the network portion in green, which is exactly what we had before. And instead of a string of 1s in the last 11 bits, we have 11 1s. If we convert that back to decimal dotted notation, 172.20.31.255 is the broadcast address that would needed to be used with the original IP we started with. Next, we did subnetting, where we created fixed size subnets, that is, subnets that had all the same number of hosts. So the example we're solving here is you're given a traditional class C or /24 subnet of 192.168.1.0, and we need to create 5 equal size subnets. So the next question I would ask is, what's the first thing we need to do? And hopefully you said figure out the number of bits we need to borrow, to which I would reply, okay, yes, that's correct. How do we do that? And your answer should be, we find the smallest value of n where 2 to the n is greater than or equal to the number of subnets needed for the smallest value of n that makes that true. So how many bits do we need to borrow? And the answer would be 3, because 2 to the 3 is 8. 2 to the 2 is 4. That's not enough, so the next one up is 2 to the 3, which is 8. So what we do is we already have our network as the /24. I'm showing the subnet bits that we need to borrow in red, and of course the host bits are still in blue. The next question we sometimes ask is, how many usable hosts are there in each subnet? And the answer is, the formula we use is 2 to the n minus 2, where in this case n is the number of host bits we have. So this formula becomes 2 to the 5th minus 2. 2 to the 5th is 32 minus 2 means that we are creating 8 subnets, 5 of which we will use, and each of those subnets will have 30 hosts. Now, anytime we subnet, we need to change the subnet mask. So we started with /24. We borrowed 3 subnet bits. So the new subnet mask in slash notation is /27. If we wanted to convert that to decimal dotted notation, like you had some problems in homework assignments, that would be 255, 255, 255 dot 224. Now then, if we continue on, for subnet 0, we start with 0 and go up. Remember, the subnet bits were in red. So subnet 0 has the binary representation 000 for subnet 0. If we want to find out the network address, we set all the host bits to 0. And this is what we would get. And if we converted that back to decimal dotted notation, 192.168.1.0 would be the network number for subnet 0. Now then, the other thing we need to know is the broadcast address. How do we get that? We get that by setting all the host bits to 1, which would give us this set of binary values. We're still doing subnet 0, so we have the 000 in red, and then we have the 5 host bits in blue, which are 111. And if we convert that back to decimal dotted notation, we get that the broadcast address is 192.168.1.33. Now, if you were asked what were the usable hosts, they would be all the IPs from one more than the network address up to one less than the broadcast address. If we look at subnet 1, notice that we now have 001 in the subnet bits for subnet 1. To get the network address, again, we set all the bits to 0. This is what we would have. Converting that to decimal dotted notation would give us 192.168.1.32. Another good check is this value should be one more than the broadcast address for the previous subnet, which was 1.31. So that is correct. How do we get the broadcast address? Setting all the host bits to 1. If we do this, this is the binary representation. And if we convert that to decimal dotted notation, the broadcast address for subnet 1 would be 192.168.1.63. And you could continue this process for either the 5 subnets we needed, which is what you would normally do, and of course you could also figure out 6, 7, and 8, which we did not need in this example. So that's creating fixed size subnets. The next thing we did is we talked about variable length subnets, and an example of that would look like this. You're given this subnet, it's Class B network 172.16.0.0/16, and you need to address all the networks shown. Now, one of the first things I would ask my students is how many networks do we need? And a lot of times they would say 5 because we have 5 clouds down there that specify how many hosts we need. But we need to realize that the connections between the routers shown as red lightning bolt serial connections are networks as well that need 2 IPs. So the correct answer is we actually need 7 networks. Now then, if you recall, the first thing we needed to do in variable length subnet mask is order the subnets from largest to smallest if that is not how they're ordered, which on the figure they were not. So that means the largest subnet needs to accommodate 300 hosts. So what we're doing is we need a subnet that has 300 usable addresses at least. So the formula we use when we're talking about usable host is solve the smallest n for which 2 to the n minus 2 is greater than or equal to the number of hosts we need. And if you go through and look at that, the answer is 9. So what that means is we need to come up with a subnet mask that allows for 9 host bits. And the way we do that is we have 32 bits. If the last 9 are host bits, then in slash notation, the subnet mask would be slash 23. So the first 23 bits would be the network portion of the address, and the last 9 would be host addresses for this subnet that needs 300 hosts. So we have something that looks like this. We have 9 host bits, and we will have 7 network bits that will be tacked on to our original 16 bits that were in the subnet network portion. So this would be asking the question, how many subnets do we create? So in this case, 2 to the n, where n is the number of subnet bits, n from the n's in the network bits up there at the top is 128. So how many hosts are in each of these subnets? We needed 300 for the first one. 2 to the n minus 2, where n is the number of host bits. If you solve that, it comes out to be 510. So what this does is this creates subnets 0.0, 2.0, 4.0, 6.0, 8.0, etc. So it is going through, and they would refer to this as the magic number, at least Cisco does, and figuring out that that's 512 host plus broadcast network. So that's going to vary the subnets, as we see, by 2. So what we want to do when we're doing this is we always use our first subnet for the largest value we're solving for. So it's going to be a slash 23, and we're going to start with 0.0. So next what we do is we repeat this for the next largest subnet in our list, which in this case needs to be 100 hosts. So again, we say to accommodate 100 hosts, how many host bits do we need? And that's 2 to the n minus 2, where n is the number of host bits, and we solve for the smallest n, for which 2 to the n minus 2 in this case would be greater than or equal to 100. If we do that, n is 7. So figuring out the subnet masks, since we have variable length subnet masks, these subnet masks may be different from subnet to subnet. So 7 host bits means we have 25 network bits. So the subnet mask is going to become slash 25. So what we do is we choose the next network that we haven't already used, which is 2.0, and basically this is what we have showing the host bits and the network bits. So continuing that on to the next page, we'll be using a new subnet 0. So we'll be setting the 2 network bits to 0, 0, and using that will give us a setup like this. And if we go up, we'll end up with the network address being what we started with, 2.0 slash 25 subnet address. Now if we set all the host bits to 1, to get a broadcast address that'll give us a broadcast of 2.127. The next subnet that we have available for use would be where we have 0.1 out of this subnet. So we repeat this again for the next largest subnet, which is 50 hosts. To accommodate 50 hosts, how many host bits do we need? Solve 2 to the n minus 2 greater than or equal to 50 hosts. What's the value of n that makes this true, the smallest value of n? And the answer is 6. So that means we need 6 host bits. So if that's the case, that's a /26. And we use the next network. The last network ended at 2.127. So the next IP we have is 2.128. And basically what we would have is a situation like this. We gain a network address because we went from a network bit, because we went from a /27 to a /26. So if we carry that to the top of the next page and ask what the new subnet 0 is, that's by setting the one network bit to 0, which is what we have here. So that's our network address, which is 2.128. Again, we determined on the previous slide that it's a /26. If we set the 5 host bits there, or 6 host bits to 1, we end up with 2.191. Our next subnet would be where we set the network bit to 1 instead of 0. And carrying that over, we would need to ask what is the next largest subnet for 25 hosts. How many bits do we need? We need to solve 2 to the n minus 2 greater than or equal to the 25 hosts we need. What's the smallest value of n that makes that true? The correct answer is 5. So we need 5 host bits. So the subnet mask becomes what? And the answer is /27, because 32 minus 5 is 27. If we go to the next network that we have available to us, 2.192, that would give us this scenario. Carrying that over, new subnet 0 would be setting the new network bit to 0. And that would give us, if we set all the other host bits to 0, a network address of 2.192/27. If we set all the host bits to 1, then we end up with a broadcast address of 2.223. The next subnet we would get would be by changing the third bit in the last byte from 0 to 1. So that would be our next subnet. So it would be 2.193. So what we do is the next subnet we need to deal with is for 12 hosts. To deal with 12 hosts, we need to solve for 2 to the n minus 2 greater than or equal to 12. The n that makes this true is 4. So that means we need 4 host bits. So hopefully you know very quickly that our new subnet mask is /28. So what we would do is we would start with 2.224, which is represented by this. We have the 4 host bits and 1 new network bit. Carrying that to the top of the page and setting that new subnet bit represented by an n to 0, setting all the host bits to 0 for the host address would give us 2.224/28. And if we set all the host bits to 1, then the broadcast would be 2.239. The next subnet we would use would be setting that network bit from 0 to 1, which I've shown down to the bottom. And what we would do, notice that we ended with 2.239. So as a double check, our subnet address for the next subnet should be 2.24. But going through the process, we have two subnets that we need to do of two hosts. This would be the first one. How many bits do we need for 2 to the n minus 2 to be greater than or equal to 2? The correct answer is 2. 2 to the n is 4, minus 2 is 2. So that is equal to 2. And that means our subnet mask for this subnet is going to be /30. Like I said, we go to the next IP address. So what we have is this. We have 2 new subnet bits followed by 2 host bits. And what we do for subnet 0 is to set those 2 network bits to 0, 0. And then if we set the 2 host bits to 0, we end up with 2.240/30 being the network address. Setting those 2 last bits to 1 means that we end up with 2.243. The next subnet would be taking the 2 new subnet bits and setting them to 0, 1, which is we're going to go through and do. So again, we need 2 hosts. We've already solved this equation. Found out that n is 2. Again, that means that we need 2 host bits for the subnet mask, or to figure the subnet mask. 2 host bits is a /30. And what we do is we choose the network address, and then we set all the host bits to 1, which would give us a network of 2.244/30, which is one more than the broadcast address of the previous address, and a broadcast address by setting all the host bits to 1 of 2.47. So I hope these examples are useful. Like I said, figuring out the network numbers and broadcast address, doing fixed size subnets, and in this last example, variable length subnets.